Good afternoon. So I'm Oliver Gao. I'm the director of Cornell System Engineering program, and we've been organizing this Ezra roundtable seminar series focused on system engineering. So today, actually, we're very delighted. Actually, we wanted to get the speaker here quite a long time ago, and finally today, Yaniv, he is here with us. So Dr. Yaniv Mordecai is actually Mordecai. He's a senior research scientist at Amazon in Seattle, Washington State. So actually he's also a senior teaching fellow at Tel Aviv University in Israel. He was the Technion MIT postdoctoral fellow at MIT Engineering Systems Lab for 2 years. Actually, it was really during that time we started interacting with him, and we really liked the research he's been conducting. So he actually holds his PhD in system engineering from Technion, Israel Institute of Technology, back in 2016, and also he got his master's and bachelor's degree in industrial engineering and operations research from Tel Aviv University. So Yaniv has over 23 years of experience across different sectors, from academics, industry, and also government sectors. He actually, his work is trying to apply artificial intelligence in complex systems, also including applications in operations research and also in model-based system engineering. So he's got a lot of honors and awards. For example, he's a member. He's a senior member of IEEE and also a member of INCOSE, International Council for System Engineers. He's also duly elected member of Sigma C. He won 2 international doctoral research awards and several best paper awards. So as you can see, that this, we are really having a wonderful speaker here. So please join me in welcoming Yaniv.
I'm really, really happy to be here. This is long overdue. We were supposed to meet last year, and it didn't happen because of the situation in Israel last year. But I'm really happy to be here today. I was given the opportunity, and I think the last time I visited here in Ithaca was May 21. Campus was literally abandoned. I was the only one on campus, basically, but now it's great to see the place, teeming, and everybody's here. And it was actually snowing, now that I think of it. Yeah. So, but now it's a lovely weather. It's really great to be here. So thanks for the very, very kind introduction. I was like, where'd you get all this data from? It's a pretty serious research. Yeah. So. On the here, yep, and then this will work. Okay, so yeah, I'm not going to go again on the introduction. I just want to say, yeah, I'm working for Amazon. It's not a secret. Whatever I'll be presenting today represents my own thoughts and opinions and perspectives. Although I do have to say that a lot of it is inspired by what I do for Amazon as a research scientist, but also by what I've been working on as a systems engineering researcher, both at MIT and at Tel Aviv University and Technion in Israel. So all of these experiences, as well as the experiences I've had as a practicing system architect, have all brought me to kind of put together this presentation. So who here is from the systems engineering department, curriculum, program? Okay, and who's not? All right, where are you from?
Mechanical.
Mechanical, it's good, close enough, okay. Basically everybody's an engineer, right? So just kind of figure this out. Yeah, so model-based systems engineering. Who is not familiar with the term model-based systems engineering? I guess, okay. Systems engineering you probably know of, right, heard of. Model-based systems engineering is basically the application of formal conceptual modeling methods with system thinking in order to specify complex systems using well-formed, well-structured syntax-based diagrams and the underlying data model that sits below that. and to gradually replace our heavy dependence on text and textual artifacts like documents with a more engineering rigorous kind of representation of knowledge about systems. And we have the cozy vision for 2025, which is just around the corner, for model-based systems engineering to become the way of running systems engineering across the board. Not quite there yet, but we're making progress. And it's not just about being able to build these cool diagrams with all these model tools that we have for like system architect and other tools for describing the structure and the behavior of the system that we're dealing with. Simulation, this is, for example, with OPM, object process methodology. It's not just about being able to describe complex behaviors, it's also about being able to make sure that there is significant ROI, added value coming out of the modeling process and the model's artifacts. And for example, in this paper from Lockheed Martin, they were able to see significant ROI from just applying model-based systems engineering and saving a lot of design bugs that would have appeared later on down the road in the integration steps. So yeah, a lot of what has been in the past, I would say, 5 years, changing how perceptions of organizations are regarding modeling in complex systems is the digital transformation. Okay, so the idea of having a whole value chain of digital research and development where everybody is based on well-defined artifacts, data-driven, decision-making, automation of processes, and everything was going well all the way up from the inception and product design all the way down to operation through manufacturing. And of course, systems engineering was slightly lagging behind until people realized that the way for systems engineers to become part of this value chain is by basically having our own digital artifacts, and what could be more suitable than the model-based systems engineering environment. And that's how a lot of organizations started, actually, customer stakeholder organizations actually started asking system vendors, aerospace and defense manufacturers, medical device manufacturers, and so on, to start generating these models in addition to whatever documents they were already generating. Yeah, so MBSE is a digital enabler, not just for the process of building the system, but also for the process of operating the system. Everything that has to do with digital twin is now become based in many ways on system models that represent the structure and the behavior of the product, of the solution, of the service, and so on. Yeah, and there was even a vision that was taking all of this into account, a revised vision for 2035 by Cozy for reimagining systems engineering as a digital data-driven paradigm for systems engineering. And then generative AI came along and started moving the cheese for everybody, not just for systems engineers, but also for a lot of other professions that have to redefine themselves. And of course, this is referring to two famous books, the Who Moves My Cheese about adapting to change, and the Black Swan about phenomena that could not have been expected or could be rationalized just after the fact. Just a strong recommendation for everyone. By the way, I generated this image with generative AI. I tried to ask it to move the cheese with a robot that looks like a black swan, but it didn't really, and I wanted the bottom of the maze to look like a SysML diagram, but that didn't really work well. Yeah, so there are probably a few iterations needed, so I just put in the black swan just for the reference. By the way, it did actually, at some iteration, put the black swan next to the robotic arm, and it seemed to be scary, so I decided not to go along with that. Yeah, so AI, let's talk about AI for a bit. Who hasn't heard the term generative AI or AI or large language model in the past 24 hours? No one, absolutely perfect. Because up until I would say a couple years ago, there was this joke, actually this tweet is from 2018 even. Does this work? Yes. So yeah, what's the difference between machine learning and artificial intelligence? If it's written in Python, it's probably machine learning. If if it's written in PowerPoint, then it's probably AI. The PowerPoint was that AI was associated with a lot of hand waving and statements, and not necessarily with actual things that we can do. And then ChatGPT came to our lives almost 2 years ago and changed everything, and started becoming a token or a synonym with generative AI and with the ability to generate content, all sorts of content. Originally, we're looking at text, but also code and data sets and images and videos and music, and a lot of different content that is not just more of the same content represented differently from the data set that we already have, but something new, something creative, I would even say, innovative, that is not directly associated with the content that we're reading, like we would in a closed model that runs over a data set. It also works together with our instructions and our commands or additional information that we provide to the model. And the beauty of it all was that we could now start providing these instructions to these models, not with coding, which required a much better skills in programming computers, but we could just do it with natural language, right? And that was, I think, one of the biggest revolutions of the past couple of years, being able to communicate with computers with text, where the main use case, I would say, has to do with language processing, natural language processing, both the language that is in the original data, the documents, the information has been encoded and read and learned by these models that the models were trained on, and the data that is provided to the model by the user. Okay. And there are, of course, all these different models for large language models. ChatGPT, that you probably know the series. Claude, which some of you may be aware of. Facebook, this is by Anthropic, and Facebook created this model called Llama, and Google has Gemini. Everybody has a model, and yeah. So here's the thing: we have been searching for ways to communicate with computers for I don't know how many, ever since we started with the punch cards in the 19th century. And all the way through various ways of enhancing our interaction with computers. And it got more structured and more fine-grained and more detailed and more precise and more accurate, until we even got to a situation where we communicate with the brain. Computers can communicate with the brain through brain signals. And then all of a sudden, all of this bubble burst, and we just said, let's just talk to computers the way we talk to each other, okay? With natural language. And that's a very big revolution. People now may take it for granted and something obvious, but it's a big change. Now, where does this meet us as systems engineering? Systems engineering is a very text-based profession. It contains a lot of textual information, in addition to diagrams and feature specifications and everything. So that lends itself pretty naturally to a profession that requires a lot of text processing and understanding. So that's almost a disruption in how we can do systems, and we are supposed to do systems engineering these days. Now, initial thoughts or maybe misguided thoughts about large language models have been that it's just like another type of chatbot, and it's not exactly, because chatbots are usually working on closed questions, and large language models are usually on open questions and closed set of keywords in chatbots, as opposed to no set of keywords at all in large language models. And actually, the interesting thing was that the chat capability that was put on top of the model, that was what made large language models so accessible to many of us, right? So we could just communicate with the model directly. And actually, at some point, the nice thing is once you realize what it can do, you can actually throw away the chat part of it, and you can just communicate with the model directly through an API. And you don't have to use chat that doesn't necessarily scale for the types of projects that you have to, the problems you have to solve. And then there was also this misconception that large language models are basically like Google on steroids, right? It's just like a very, very strong search engine, and that's also not exactly true, because search engines like Google are not supposed to generate their own content. They're supposed to point you to the right content, and large language models can actually synthesize a lot of this content and generate some content of themselves, depends on how much creative you want the model to be. And I don't know if you guys noticed, but you could probably see that if you search for in Google, for example, these days, you can also see a small, short summary that's coming up at the top and kind of giving you an overview. In my opinion, that could break Google's model, because then who would want to click on the links down below? But maybe they have a solution for that as well. Now, so once you understand what these models are about, the ability to generate content, there start to come up all these different user requirements that we are, of course, as systems engineers, always very thoughtful about. So users want to be, this from the literature, but you can also probably see what you would want to see in an application of a large language model or generative artificial intelligence that you would build for use, right? You want to be able to provide instructions. You want to be able to provide additional resources, not just your basic instructions, but also additional resources that are coming in from files, from databases, from data sets, from the internet, and so on. Try to ask ChatGPT what's the weather today. Doesn't necessarily have an answer. You want to be able to communicate with the model, improve and refine inputs and outputs. You want to be able to explore the different alternatives. You want to be able to receive explanations, because a lot of the outcome that's coming out of it doesn't always make sense, doesn't always seem like the best. Like, why did the model come up with this result? You want to be able to understand. You want to be able to further discuss and clarify things after you understand why the model reached a certain solution. And you want to be able to do all these things at scale, which is basically means to automate processes, to manage all this interaction. You want to store everything you've communicated with the model and then be able to retrieve it later on. And of course, scaling, run the whole thing for enterprise applications, not just for you and I when we're sitting in front of our computer and trying to get some answers to an assignment that we got from our professor last night. So now we have to understand that these models also have a lot of limitations, okay? We have to be very careful with the hammer paradigm. You know the hammer paradigm? When you have a hammer, all your problems start looking like nails. So we don't want to try to solve all the problems in the world with these models, although a lot of people are trying. And we're talking about well-defined tasks, deterministic processes where you have to have repeatability in your results, in your processes, real-time decision-making. These models take a few seconds to return an answer. Sometimes you need milliseconds. That might not work for you. When you have structured data analysis that you can apply well-defined data analysis models for, SQL, for example, or other sorts of tabular data manipulation and processing. You have strict requirements on AI visibility and regulation. These two often come together, especially in industries like healthcare, medical devices, aviation, and so on. When we're talking about resource efficiency, these models are not so resource efficient. There's progress being made in that regard, but there's always room for improvement, especially if you have to run it on an embedded device, for example, or IoT. They don't always have the capability to run all these different, all these models at the edge. By the way, I just read that Oracle is building a nuclear power-generated AI center, a data center. So I'm curious to see how that would kind of tilt the power balance there. Budget constraints, these things could be expensive, both to develop and use on a day-to-day basis, and domain-specific knowledge, like in space exploration or other very unique areas. And I think I would assert that systems engineering itself is still somewhat of a domain-specific knowledge, because it requires both very good understanding of methodology and very good understanding of the application domain. And that's why this coupling doesn't always render good results when you're working with these general purpose models to get answers to questions related to systems engineering. So once we understand what we want and what are the limitations, what are the typical use cases or applications for large language models, we're talking about things like basic fact search, text generation. It's pretty good in translation. It's pretty good in summarizing content that you're feeding into it, rewriting it and rephrasing it, fixing typos, stuff like that. It's pretty good in classification, taking structured data and turning it into structured attributes. I will show some examples later. It's surprisingly pretty good in sentiment analysis, in understanding whether the text represents positive or negative sentiment by the author. Obviously, as you see, it's good for enriching conversational AI. Now you can see that if you communicate with your airline company or your insurance company, they already start putting in some AI into their chatbots and making them much smarter. Also capable of achieving some results with agents that have the AI capability. It's good in plagiarism and similarity analysis, so watch for that. It's actually pretty useful, although I have to admit that sometimes it hallucinates and comes up with papers that never exist. I can attest it to myself. I asked it whether I wrote the paper and said, yes, you wrote the paper called whatever, about quantum something, which is completely not true. And of course, it's very, very good in code generation. So, okay, yeah, so once we understand how this works, we want to be able to scale this into a full-blown solution that is part of a bigger system or that is a system in and of itself. And there are all these hurdles and barriers towards the integration of generative AI. It looks nice, it looks promising, but if you want to make it part of your solution in let's say, aviation or healthcare or energy or whatnot, this could start becoming a very big challenge to solve. Because usually you start with isolated proof of concept models that are very hard to integrate later on with enterprise applications. There's always issues with performance and latency. Security and safety, of course, always are concerned. Programmability and the ability to control how the model behaves for different use cases and scenarios in the field. Because when you run these models on lab-tested scenarios, it's not always a very good representation of what it looks in the field. Genericity versus fit for purpose. So you can build a very good fit-for-purpose model, but once you move a little bit to another application, then it won't necessarily work for you. Let's say you want to adjust your model from taking care of customer support and, let's say, billing or something like that versus technical issues, right? That's a whole different model you need to build. Predictability, especially when you have to make sure that the results will repeat themselves for exactly the same scenario, for exactly the same input. These models, depending on how you are calibrating their creativity levels, could generate different results. I mentioned safety. Scalability itself is also still, these models always have limited quotas and processing bandwidth, and then this also becomes a big issue. And all of these different concerns are causing like these two opposite trends where on the one hand, you can see that there is, who is not familiar with Gartner's hype cycle? Okay, so the hype cycle basically says that every new product that is introduced into the market is looking something like this, okay? And this is called the hype cycle. Because there's a new technology, everybody is so excited. First of all, nobody understands what it's doing. Then people start figuring out what it can do. Then there's like all this excitement and hype, basically, and then people starting to understand this is like the trust of disillusionment, and then it starts to kind of balance into like this stable, reasonable sweet spot of use cases and applications. And the thing is that people are starting to kind of feel this disillusion with generative AI. The problem, or the nice thing about it, is that this is progressing and advancing at such a rapid pace that it keeps beating its own hype cycle and basically resetting it. So this is, for example, from last night. Okay, last night, while I was kind of touching up my presentation, I decided to add this slide. OpenAI announced a new model called Strawberry, which is showing you its process of thinking. I don't know if anyone had a chance to test this out yet, but it's incredible because it shows you how the model itself is thinking. And if you can understand how the model is thinking, as opposed to being a black box until now, where you could ask it to provide you with some information about its reasoning, but it was still a black box. Now you can actually see a white box. You can actually see, and if you can see the white box, you can actually interact with every step of the process, right? So that gives you a whole different level of control over these models, and that would not necessarily solve problems with adoption that I mentioned as a result of what I showed in the previous slide, but it could definitely open a hatch for additional use cases, additional applications, and so on. So how does all of that have to do with systems engineering? Right now, you can already use these models to generate requirements. You can generate specifications and list of features and of what your product and solution can do. You can generate design, solution, architecture. You can generate code that will go into your product, and you can even generate tests for your product and for your application, and test scenarios and test plans and so on. And why am I just talking? We said that it's no longer about PowerPoint, right? Let's give you an example. So I decided to come up with this crazy idea of, if you're a great Costco customer, you probably know why I would need a robotic arm at the trunk of my car so that I'll be able to load and unload all the things I'm buying at Costco when I get home. And I just came up with this crazy idea. I want a car with a robotic arm. Just said, give me 10 requirements. Of course, I could ask for more. Give me 10 requirements for a car that comes with a robotic arm, that can pick up things and store them, blah, blah, blah. It can pick up, I just give it like very, very crude requirement here that it can pick up from the road or from a table and put it back and so on. And it starts generating like these 10 requirements, just captured 5 here. But you can see how it gives you like a very good starting point. It's not optimal, it's not ideal. It could probably be much better and much more precise, okay? But notice that I didn't provide any context other than just car with robotic arm. So it was already capable of understanding what a car is, what features cars have, and then what's a robotic arm, what features robotic arms have, and then how do these two things work together. So for example, things like load capacity, right? This is critical both from the car perspective and the robotic arms perspective. So we talk about load, volume, stuff like that. Okay, all of these things have to be taken into consideration. Working in a much more contained environment, whereas these robots that have worked in a production assembly line, stuff like that, right? So notice that we didn't provide anything else in addition, and we already have a good starting point. Of course, if I provided all the requirements I already have, as I will show you in a moment, then that would the model would be able to provide much better and much more focused requirements about what still needs to be done to basically create a more comprehensive and complete requirement. So yeah, so not just requirements. Let's say I'm not an expert, I just have a very cool idea and I don't exactly know how to deal with all the safety issue here, right? So I asked it, can you give me a list of the safety protocols that this product will have to comply with? So it brings me a bunch of protocols here from various standardization bodies, right, like ISO and the federal standards for motor vehicles and so on. And basically now the thing is that behind each and every one of these protocols, there's a whole set of additional requirements that need to go into into my solution so that it will comply with these standards. So basically now I can drill down into each and every one of these standards and take all the specifications that it contains and transform them into requirements for my own solution. Okay. Now, basically, if I hadn't told them, you saw, for example, here that the model was giving me like this high-level requirement for safe handling, right? So I still need to understand what safe handling means. I still need to understand that it means, for example, being in compliance with these motor vehicle safety standards and robotic safety standards and the combination thereof. And I can also generate an initial conceptual design. What do you know? Again, image generation, I said I need a car with a robotic arm. So it gave me a car with a robotic arm. And as you probably can see, the robotic arm is not in the car. So I told it, no, I need the robotic arm to be in the car. So now the robotic arm is indeed in the car. But I said, no, I mean, the robotic arm has to be inside the car, and it just gave me it from another angle. So no, look, you didn't understand. It needs to be, the base of the mount of the robot needs to be inside the car. So of course it blocked all the trunk now. My idea was like that it would be kind of hanging from the top here, because when you open the trunk, you want it to be kind of like on top of things, and then it can kind of see what's going on, and then the manipulator can move around and lift things. That's kind of what my thought. And I actually told it to the robot, and then I was hoping that it will finally get what I'm trying to get at, and it just did that. So it's not perfect yet, okay? Maybe there are other better solutions. Of course, this is just from ChatGPT. There are models that specialize in these kinds of designs. But what it did remind me was a very, very famous children's book called The Little Prince. Why did it remind me of that? Because of this, draw me a sheep, the little prince said. And after a few iterations that the narrator did with the little prince, he eventually drew this box and said, you know what, your sheep is inside the box. So now you can imagine it whichever way you want it to be. So, of course, another read recommendation, or you can read to your kids. But yeah, so what I did next was to say, okay, ChatGPT, draw me a sheep. And what did I get? I got a sheep, because that's what I was asking for. It's very good in following instructions, by the way. But what I did next was to say, hey, dude, don't you know about The Little Prince by Antoine de Saint-Exupéry? And he said, yeah, of course I know about it. Here is The Little Prince. And it even realized that since I was asking it to draw me a sheep, it gave me this paragraph about the famous scene from the book about drawing a sheep. And then I said, okay, can you now draw me a sheep? And this is the result. So it's a sheep inside a box, okay? So it figured out the reasoning here. It's not still perfectly aligned with what I wanted, but what I'm trying to say here, and this is how it relevant to systems engineering, is that it's all about the context. If you give it additional context about your system, about your environment, you can generate much better results. You can generate progressively better results if you understand what you're talking about. And this is still not perfect. This will still require more iteration, but you see where we're going with this. And for context, by the way, any questions so far? Okay. So, and for context, we have to understand what is the system, not just what is a system, because anybody can define a system as a combination of elements working together to achieve a common goal. But when we're asking what is the system, we often need to understand that it's not just about the core system of interest that we're building, but it's also about the system that builds the system. We call it system 2, or the engineering system, and system 3, which is the system that operates, all right? So this could be, think about it as the city or the university, and this is the R&D organization, and this is the product or service that we're developing. And you can see that MBSE modeling and simulation basically pertains to this tier 2, the system 2, because it's part of the development process, where this GenAI is actually an operational tool. I mean, you saw how I'm interacting with it to achieve goals. And imagine that I was a digital content creator. That's what I would have done every day. So it's an operational process. So the challenge is in figuring out how to cut across this boundary and bring in these additional context into the GenAI process. So this gives rise to the need to start thinking about these two technologies together, about coming up with synergy, not just understanding what each and every one of them does separately. And that gives rise, of course, to some kind of SWOT analysis, strengths, weaknesses, opportunities, and threats. Some of these weaknesses and threats I've already mentioned. I think the biggest threat that people are concerned about is the potential for job displacement, or like whole jobs being vanished. I don't think it'll happen that fast, or I think various jobs will reinvent themselves in light of the ability to generate content much faster than we used to. For example, generate a specification that would have taken months to achieve, now it can take weeks or even days. And of course, resistant to change, I already mentioned who moved my cheese. But in terms of the strengths and opportunities, this is where I want to focus, of course. I think that the main thing is that once we start putting these two technologies together, it gives rise to the co-evolution of both of them. So AI will start being more fit for the purpose of generating system models, and system models will be more fit for the purpose of being informed by AI insight. And of course, it will lead to continuous improvement and to new design paradigms. So the whole design process will now become, I would say the AI part of it will become embedded in the design paradigm in a much more practical way. We had all these different examples of methodologies that would contain AI in the past. But again, it was a lot of hand waving because we didn't have compute power, we didn't have data, and now we have both of these, and this problem is basically solved. So let's talk about scenarios, right? So the basic scenario that you would see, so this is a model, this is a SysML model, for those of you who are not familiar. This is called an actor, this is a block, and this is just representing how you would interact with a model, just like I just showed you, right? I mean, I'm giving the model a prompt, I'm getting a response. The response could be a set of features, functions, requirements, and so on, safety standards. And then what I would do is go into my other tool, could be a model-based system engineering environment, could be my Canva, could be my notebook, could be whatever, and then I'll just transform the concept that I have in mind into something that is a digital artifact. Okay, that's the nominal process that we almost do every day. We read data, we read articles, we consume information, and then we come up with our own ideas and kind of formulate. But we can do something more sophisticated than that. What we can do is to augment our prompt that's going into the model, not just with our instructions and thoughts, but also with data that is coming in directly from the model. So these large language models can actually read digital artifacts like model-based SysML models, for example, or textual specifications, and grab the context that was necessary for the chip in the box, right, out of these models. And I'll show you an example. And then you can start generating artifacts into an artifact repository, and you don't just interact with the system engineer. Everything that you're generating gets stored as another type of digital artifact. Okay? And then there's an even more complex or sophisticated way where the model, the GenAI model, doesn't only consume context from the model, from the digital artifact that represents the specification of the system, it also feeds back into it. Okay? Feeds back into it. This requires this engine to have some kind of interface, and for this mechanism to have some kind of interface that it exposes for this model to be able to communicate with it, and to guarantee that whatever is going through this direct line of communication is valid, robust, well-tested, because if we start injecting new knowledge, new content into our model without control, that could be a problem. Of course, this process can be moderated by the system engineer or by whoever is the stakeholder of the process. But this is the next level, and we're getting there, especially for simple tasks. How much more time do I have?
You at least have 10 more minutes.
10, okay, I think I'll be able to finish. Yeah, so basically now we're looking at the synergy of these two technologies, with the system engineering being the beneficiary in the middle, not necessarily the interface between the two, but as the beneficiary of their interaction, where generative AI can help us with tasks like automation, gap and risk analysis, summary and explanation of features, for example, and managing the process according to some well-defined methodology we want to use. But we must not forget, as systems engineers, that MBSE can still help us very much understand and build solutions that contain generative AI applications. So there is a two-way process here where MBSE is not just benefiting from generated content about the system of interest, but it can also inform the architecting of these systems, which is always somewhat of a problem. And I can tell you from a friend of mine who used to work for one of these companies, never mind which one, that it's a mess behind the scenes. What you're seeing in the front end of the website looks like very nice and shiny, but it's a whole mess behind the scenes because these models were not built with the best practices of system architecture in mind. So when we're talking about the co-evolution, I think there are two things we need as a community or as an ecosystem. One of them is for a body like INCOSE or maybe ISO or maybe the OMG or some other standardization body to build a consortium of government, industry, and academia that will build a dedicated foundation model, so the model that is trained on content, that is not the common model that we're using today for all these general purpose tasks, but something that is much more fit for purpose for system specifications, design patterns, much more detailed information about system modeling. Okay, this will be very helpful in generating much better results. on the one hand. And on the other hand, I think that the tool vendors that are building all these tools need to start understanding how they're injecting these new features directly into their software, so that I don't need to go out into an external tool like ChatGPT to ask questions about my model. I need to be able to do this inside the ecosystem that I'm already in, so that I don't have to look around the corner for other solutions. And that's doable. I think that once this is done, it will also pave the path for a direct interaction of the GenAI model with the model inside the model-based systems engineering environment, and it will be able to directly inject modeling constructs into our model. That will close the loop that I showed you, scenario number 2. Yeah. And then there is another thing that's coming together, and again, I mentioned it in the context of MBSE assisting GenAI, the role of the AI systems engineer. I don't know if you guys started seeing these kinds of opportunities, career opportunities, but you need to, as an AI system engineer, in general, systems engineers who are working on AI-powered systems will gradually become experts or sources of authority about how to integrate AI into solutions. They will need to take care of all the processes in the engineering ecosystem. They will need to take care of services like modeling, simulation, testing. All of these things need to be well designed, well defined, because if you want to integrate these things repeatably, then we need to have a much better methodology basically to work around these things. And we suggested this methodology. We came up for something else, but I think it also works for this. You can see, for example, in this very basic or crude architecture of a solution that is powered by AI, that eventually the AI piece of it is just like this little box here. All the rest of it is still like very much standard, typical system engineering or system architecture that you need to understand about, a few things about. And then eventually there's just this like automated process here that replaces some other kind of reasoning model with this open model that generates results that are more suitable, for example, for text. In this case, for example, it's an FAQ service where you ask questions about papers, and then it gives you the result, something that was much harder to achieve with the closed models, even closed natural language processing models. See, like the box here at the bottom is just one of all these different items that we need to get into our architecture. So who cares? Who takes care of all of this, right? I mean, maybe there are some AI experts around here, but who make sure that all of this is interconnected? Okay, so some examples. I was talking about generating requirements, and indeed, one of the studies that we've done, a student of mine presented it in IEEE Aerospace 2024, a few months ago. And he was capable of showing how we can generate requirements for an input that contains an initial set of requirements for an IoT system, and based on the initial model-based design of the solution, it was able to also classify the requirements into the different functions or subsystems. For example, sensors, processors, actuators, communication, energy, and so on. And the nice thing about it is we're able to show to generate requirements for like all the different types of requirements, functional and non-functional alike, performance, scalability, legal, all sorts of requirements here based on the initial input, even when the initial input did not have, for example, legal requirements. Okay, see, for example, if we didn't have any legal requirements, we're still capable of generating legal requirements. Okay. And we were also able to classify the requirements into the different subsystems, so that's also very helpful. When you have an initial set of requirements from your stakeholders, they don't know about the system's architecture, but you need to start transforming them into system requirements that are coupled with the functions or the subcomponents of your system, so that you'll be able to start allocating these requirements to the different disciplines and the different professionals that have to eventually implement these requirements, right? Make a system out of them. By the way, we also worked with a very common database called Promise. Maybe some of you are familiar with it for IoT requirements. And one very nice thing we were able to do is, sorry, this is actually for software requirements. And what we're able to do is to augment this database with a bunch of new IoT requirements that they did not have before, because IoT also takes Internet of Things, right? Takes care of the hardware, the communication, the edge computing, all these different energy, all these different considerations that go into products and solutions that eventually have to sit on your wrist, right, and sense your biometrics and so on and so on. So here's an example of how we generated requirements based on an input requirement. So this is the input requirement. This is like 3 output requirements that were generated, both in traditional natural language processing methods that we use as a baseline, and with generative methods like here. And we can see the outcome here. For example, this was the input, the original requirement. The software should support integration with various sensors, and then relevant machine data. This was for machine, like industrial machine health monitoring. And then the new requirements, the software should have a modular architecture to incorporate new sensor, and software should provide a sensor calibration feature to ensure accurate data capture. So see, like, we didn't think about it. And by the way, this was evaluated by a group of experts in the field, and they said, hey, you know, okay, half of the requirements already exist, that's okay. But you know, we have all these different requirements that are great and should be added, or good and require some small change, and then there'll be very good requirements. Basically, think about all of these requirements as things that we would have missed, which could have caused project overruns, budget overruns, delays, and so on. Okay, so you know that, and you see the error here, or the inappropriate output is very, very low. We could classify the requirements according to their systems and requirement types. And another process we could achieve was, after we realized that the process of generating requirements has to be adapted for every new system development project that you're building. So we came up with this approach called generative requirements engineering, where the process is taking care of itself first, basically meaning we're adapting the requirements generation system that is based on AI, but not just on AI, but also on additional components, as you just saw, for generating requirements for the specific project I'm working on. So if I just moved from IoT to, let's say, aviation, okay, now I have to make a few adjustments to my solution so that it will be more suitable for generating aviation-related requirements. So the process is first to generate requirements for the requirement generator to adapt itself to generative, see where I'm going with this? To generating requirements for aviation, implementing those requirements in the model itself, in the mechanism itself, and then using that in order to start generating requirements for an actual aviation project, whether it's avionics or aerodynamics or engine or whatever. Okay, so that's a dual process that takes care both of itself and of the system of interest at the end of the day. Okay? And again, we were able to show, compared to the traditional approach that does not take into account this additional step, we were able to show increased value in the number of good requirements that are being introduced by the model. So a model that is better fine-tuned or trained or informed about the specific field of application is obviously outperforming a generic model, and even this is not just a generic model, because it's a generic model that was adapted to work on requirements in general, right? So you see how this is improving here, 125% and 110%. Yeah, and then do I have time for a quick demo? Okay, so I can show you a demo. Another application of a student of mine has to do with safety analysis, especially for safety critical systems in aviation, for example, is obviously one example, missile defense. And the idea here was that, as I said, we can grab the initial set of system functions or subsystems from a model, use a language model to generate this, to transform this into a structured data set, okay? So you can see how this becomes that. What are the functions in the system, okay? And then, once we have that, we can inject it into the set of requirements that we have in order to classify our requirements, not according to a hard-coded set of functions as we had in the previous, but actually in a fully dynamic interaction with the system model. So after I updated the model and figured I need a new component that was not there before, now it will automatically get injected into our input set for the next cycle of requirements review. And if I see if I can quickly show you that demo. So, of course, as I mentioned, once you realize you can do all these cool things, you don't need the UI anymore. You can just do it with very, very, very simple programming. Okay. So, So basically, what we do is we initiate the process with, in this case, ChatGPT. This is the prompt skeleton. So we inject. First of all, these are all the instructions, and we inject examples. And then we populate the downstream with the additional requirements that we brought in. So here's the initial set of requirements, okay? So 42 different requirements for different systems. We want to classify them according to the subsystems. And we want to also identify whether we have any contradictions, because this is safety critical. We want to make sure that one system is not trying to generate requirements that would conflict with the other. So, basically, you see, okay, again, you see the functions are being brought in here from the model, the MBSE model, and then we're running this model, or this is where it's running, and this is the results that it's generating. So for every requirement, okay, it gives me what function it identified that the requirement belongs to, okay? What is the type of requirement? I didn't mention it, but we also have, in safety analysis, we have functional requirements and probabilistic requirements. So some of the requirements refer to the option or the possibility of something bad happening, and we have to take care of it. And we also want to make sure that every component in the system has at least one probabilistic requirement. So that's a way for us to enforce this. These two columns are actually, this pretty important to understand. We're asking the model to provide us with its own confidence about its own answer, and with an explanation for why it reached. So we were kind of hacking the explainability thing just before OpenAI actually rolled it out as a built-in feature. So if you ask the model to explain why it reached the result, it will give you a good explanation. This requirement contains the probability, blah, 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 so it's probably a probabilistic requirement, so on and so forth. And we also ask for contradictions. So you can see, for example, here, that requirement number 16 is in potential contradiction. We're not sure, it's a 90% confidence level with requirement number 30, and obviously requirement number 30 should be in potential conflict with requirement number 16, so that works, okay? So we can actually start matching these two requirements and seeing why they would be in contradiction and figure out a design solution for this, okay? And eventually matching it with the requirement itself, okay? So now we have a classification of the requirements. We have the ability to start testing out the output to make sure that every function has requirements of both types, okay? So you see that some don't, which is not good. So this is a constructive approach that helps us understand where we need to focus, where we need to build more requirements, okay? You can also see that some of these are unidentified, so we have to make better phrasing of some of the requirements so that they'll be easily identifiable by the model. And then you see, for example, each function, how many requirements it has. And of course, you can draw a nice diagram to see whether some features like PEA, which stands for, I think, pyrotechnical and electrical activation or something like that, does not have requirements. That's not good, right? So we need to build requirements for this model, for this subsystem, I'm sorry, okay? And eventually, it also gives us just the gaps, right? These are the gaps. The PEA does not have requirements. This one doesn't have enough requirements, and this one is like the errors. So you see that there are two errors that you need to populate. And finally, the contradictions somewhere down here. And the anomalies, it filters just the requirements that are not in compliance. These are the two requirements that I need to focus on. So it kind of helps me focus on the things that I need to focus on. Once I get a better understanding of what dynamic adaptation means, which sounds like a very high-level understanding or specification that is not precise enough, then we can use that and generate a much better system architecture, okay? So basically what I'm showing you here is how we can use these two approaches together, not one against the other, not like one of them is moving the cheese for the other, but more like a dance or an interaction that is synergistic in itself with both the system engineering as a profession in itself, generative AI as a technology, and modeling and simulation as another technology. And I'm talking about something that I call socio-technical intelligence. It interacts with the concept of socio-technical systems, where we emphasize the interaction of humans and technology, and this is very much the same, where we're not interacting just with artificial intelligence from GenAI, but with a sort of intelligence and reasoning capabilities and logic application from all sorts of different technologies that could be introduced into this environment. We're talking about adaptive decision making, continuous learning, knowledge transfer, and all these generative processes of systems engineering that are listed here. We're applying this both at the system of interest level and at the system development process level, system 2, and at the operational process. So think about like this is the city or the university, this is the development organization, and this is the platform that we're introducing. So to conclude, the future seems a little bit better now, I hope, because it's not about two technologies competing with each other, but more about the fusion of these two technologies into a new paradigm that I refer to as socio-technical intelligence, where we actually benefit from having both of these human-supported automated reasoning and human decision-making supported or informed by automated reasoning itself. Maybe I said the same thing. Anyway, and vice versa. So, and from tools to partners. Not thinking about these tools or these methods, because I'm always about the methods, I don't care about the tools. The tools can change any day. Some other tool can come around the corner and basically replace the tools that we're now seeing. It happened with basically almost any methodology we've seen. So it's not about the tools, it's about the methods and about the mechanisms that we're using as partners in the processes, as these entities that we're interacting with. We call them agents, right? So they are achieving goals for us, they're helping us fulfill some tasks. Of course, we have to understand which tasks are the ones that are most suitable. Storing data about the system is obviously much more obvious when we're doing it with MBSE. Reasoning about things that are missing, concepts that are missing in the architecture, GenAI, and the combination of the two of them can help us do this gap analysis, this process management, and this continuous improvement. And these are some references, and basically I think I'm done. So if you have any questions, I'd like to take some questions. I hope to take some questions, or if you just want to keep the discussion, reach out to me on LinkedIn or through model-based systems engineering at gmail.com. And that's it. Thank you very much for staying 8 more minutes.
This is wonderful. 2 questions. I believe there must be a lot of questions. Anyone? Oh,
You said one of your recommendations was for a consortium to put effort into building a foundational model for systems engineering. Is that meant to be sort of like to establish industry standards? Are you thinking like an actual tool? Is it an interface? Like what did you mean by a foundational model?
So how was OpenAI's ChatGPT model built? They just read a lot of data from the internet, okay, and trained their model on it, created. I don't want to get into the mechanics of how these models work. They basically vectorize the whole model, giving values that help us later on analyze similarities between text and predict the next word in a sequence. Don't want to get into the details, but they just read a lot of papers, right? Now, they read a lot of papers, that brings a lot of information that is not necessarily, it's noise. It's not necessarily relevant for what we're after, okay? Building new systems, okay, and operating them. But if we are focusing just on this data set or just this knowledge base, right, we can get much better results. Now, it may not have good knowledge about, I don't know, natural phenomena or other types of processes that are not in the core of systems engineering, but we can always augment it, or what is more important, and that's how it's done, by the way, is that human auditors are actually sitting on these models and giving scores to different labels to make them a bit better at some very typical common tasks that they have to achieve, like passing the bar or like the medical qualification exams or whatever. So, or getting admitted into Cornell, for example, right? So, or like any Ivy League. So we have to make sure that these models excel in tasks that we care about as systems engineering, because we need to do these tasks anyway. I still need to generate requirements. I still need to generate specifications. I still need to do design reviews. I still need to do an integration plan. Of course, depending on the step in the life cycle of the system we're in. But we need to achieve these tasks, right? That's what our models need to excel in. And if a group that I don't identify anybody else but in COSI as a leader of a consortium will generate this model, which has to be open source, which has to be publicly accessible to everyone, and then you will be able to build your own model on top of that, right? Rather than on top of a general purpose model like ChatGPT that is good for basically a lot of applications, but does not excel in one specific application, just like I showed you with the images, right? And I think I would be even critical about what the quality of the requirements that it generates, right? Because I think it's based on a lot of common knowledge that kind of gives a lot of noise around things that you're really focused on. You have to know what to ask in order to get the right results. And by the way, I think we are still a generation that knows to evaluate the outcome, right? How would you test these models? You would usually ask a question that you know the answer for, right? So that's how you validate whether the model makes sense or not. We're still a generation that knows how to do that. I sure hope that the next generation will not just take these answers for granted, because that could be very dangerous to society. And part of our role is to make sure that they can trust these models, but also that they can criticize them continuously so that they can keep getting better. Did I answer the question? I don't know.
Okay. Questions? I have one.
Wait, I think the lady here.
There was one? Okay, go ahead.
If a lot of the examples that you might want to feed into train a systems engineering specific LLM would be not public because they're from companies, because companies are typically the ones who are making really large scale big systems.
That's why the companies need to be in the consortium, right? So that they'll benefit. Now the good thing here is that the way these models work is that they sort of anonymize the information so that it's not directly traceable to the specific. Like if you say, no, I want to understand how this actually works in the, F-35 program, right? Then the model won't let you get there, okay? It's too specific. But there are additional ways of making sure that the data is sufficiently anonymized. Anonymized in not in the sense of personal, but in the sense of let's say the identity of the systems or the functions that are involved. And of course, they can always, keep any very, very sensitive and proprietary information, matters of national security, stuff like that, in their own hands, and then they can use the basic foundation model and in conjunction with information that they have internally to fine-tune the model. So those are the kinds of things. Again, if we had to settle on some very good common basis for, I would say, cyber-physical systems or socio-technical systems, all these interactions are pretty much similar, right? Okay, so maybe it won't be ideal for, building submarines, okay? But, submarines are eventually a class of systems that are cyber-physical and socio-technical. So that could have a lot of value in and of itself. So the companies will have to kind of give a hand here so that will get valuable insight, because they'll be the beneficiaries of these models themselves once these models are available. Over.
Yes. So I think in your the generative requirement engineering in that paper, so you were trying to probably train the AI to generate requirement that it will be to your satisfaction. So in the end, the best requirement that was generated by AI, general AI. So how satisfied were you, in terms of percentage?
How, sorry?
How satisfied were you,
Oh,
with respect to
yeah,
this
so I think, we didn't judge the model on how well it was improving itself. We judged the model on how well it was improving the final result, right? So, by the way, maybe that's another metric we have to track, but I think if you're able to show that the number of the number of requirements you're generating is higher, so that's your score, like more requirements, more information about the system equals better, I guess, right? So if you're able to improve, and you're also able, you see, I didn't mention that, but we're able to cut down on bad requirements, so on this specific application from 5 to 0. Okay, so I don't even know if that's like, how do you calculate the percentage here? It's division by 0. But anyway, I have to ask the student how, what's the deal here? But anyway, yeah, it's like we reduce the number of bad requirements by 100%, and we improve the number of good requirements, right? So that's a value. Now, I don't necessarily get into the details of the requirements themselves. Like you have like a brief example here, right? For example, I would say that requirements should be specified as shall statements, okay? Not as should statements, because should means optional. So maybe our prompt needs to be further tweaked so that requirements will be more clearly specified according to the best practices of specifying requirements, right? So in terms of the content of the requirement itself or the articulation requirement, maybe there is room for improvement, okay? And of course there's the semantics, like what does it actually, eventually what we mean is we have a sensor calibration feature, okay? Let's forget about the should and the would and the shall and all of these things, right? I mean, this is the key focus here. This is the function that I will need to integrate. So whether or not this function is critical or not, I think the evaluation of the evaluation comes from this great and good and bad, right? I mean, so of course the better the rate of great requirements, right? That I think is also critical to assess. When we were introducing the generative model here for requirements engineering, we also wanted to show the added value of like optimizing the generation process itself for the specific application we're working on. But I think overall it's also important to see that you're generating a lot of new requirements from the initial information that you have. So I think that would be more like the metrics. We're tracking, we also wanted to make it a bit more quantitative because it's hard to assess the requirement whether it's good or not in terms of the language content that it has. But it's a good point, valid point.
Thank you. I know we're out of time. Let's thank Yaniv again. That's great talk. Thank you.
Next time we need an hour and then
Yes.
one run into time issues.